Hello, my name is Taishi. I am a rising senior in operations research and financial engineering. Over the summer, I interned in the mathematical modeling division at the Oxford University Clinical Research Unit, which is based out of Vietnam. And this was done under the supervision of Dr. Mark Choisy, who's the head of mathematical modeling there. So my project focused on developing a temporal spatial model of measles epidemics across Vietnam. So, as many of you may be aware, the measles vaccine has really been available pretty widespread since about the 1970s. But despite this, it still remains a very high cause of mortality in developed nations, especially among younger age children. In particular, Vietnam, in this case, has been experiencing outbreaks or resurgence of outbreaks since about 2005. To give you a particular example, in 2014, there was an outbreak that spread to about 24 cities, including the major transport hubs of Hanoi and Ho Chi Minh City, and it infected about 15,000 people, and there was about 150 fatalities associated with it. What is interesting about this is that Vietnam has a vaccine coverage rate of 95%, which is generally considered the threshold required to establish herd immunity for really any general infectious disease. But this recent spate of epidemics that have really been popping up since 2005 seems to suggest that the measles epidemics in Vietnam violates traditional assumptions about vaccine control measures. So to sort of investigate this first, my supervisor, Dr. Choisy, actually identified a particular discrepancy. And this discrepancy in the data that's available. But this discrepancy was that the officially published vaccine coverage rates of 90 to 95%, which suggests herd immunity in Vietnam, was very different from the vaccine, or I guess the population protection levels that Dr. Choisy's team actually tested in the population, which was around 60 to 70%. And this discrepancy, in fact, was particularly pronounced in smaller provinces in the northern part of Vietnam. So I'll just highlight them here. And the discrepancy was far smaller in the larger population centers of Hanoi and Ho Chi Minh City. Furthermore, what they observed was that the measles epidemics actually follows a particular pattern. And this pattern really starts off by having small epidemics in smaller populations. These epidemics typically fizzle out very quickly, but there is small probability that these epidemics reach the population centers through small connections they have. Once it reaches these larger population centers, we generally have a larger outbreak, and from these larger outbreaks, we spread to other provinces, and then we have an epidemic across Vietnam. So what I was looking at and what I wanted to really get to the bottom of is, well, how do we efficiently decrease the probability and severity of measles epidemics across Vietnam by using vaccine control measures that take into account the differential vaccine coverage rates that we see across Vietnam? And what I mean by this is we have low vaccine coverages in smaller populations and high vaccine coverages in higher populations, which essentially resulting in these patterns of epidemics over the last, I guess, 15 years. And any effective control measure should really take this into account. Ideally, we would have universal vaccine coverage. That is, we would vaccinate every single person that's able to be vaccinated. But given budgeting constraints and community outreach problems, especially for smaller provinces, this is not really a feasible method to address the problem. So what we essentially thought was, I guess there are two ways we can address this problem. And this gets to the crux of why I did this project. We can either increase the vaccine coverage in highly dense population centers like Hanoi to decrease the probability and severity of these larger outbreaks. Or we can actually target the smaller provinces and increase their vaccine coverages to a higher point to actually lower the probability that these small epidemics that rise will even occur, and in particular will spread to the large population centers. So one of them, we're looking at small populations, and the other one we're looking at the larger populations to stop the larger epidemics. So to answer this question, I essentially developed this model here, which incorporates individual level mobility data to essentially characterize the connectivity patterns between the different districts. And the idea was that I would simulate measles epidemics in this model that I have with varying vaccine control measures that I think are appropriate and see which one optimally decreases the probability and severity of these outbreaks. So essentially I broke this down into 3 parts, and we can see this with our research objectives here. So the first one is actually developing the mathematical formulation of the metapopulation model. And this involves actually quantifying the connectivity between districts, which turned out to be particularly difficult given the dearth of data that was out there. Then the next step was, well, implementation of this large-scale simulator. How do we efficiently implement it so that it's possible to do it on such a large network? And what I mean by large network is 710 districts with an average population of about 120,000 people in each district. And generally speaking, a direct simulation of this is pretty infeasible, given computational time constraints. And then the third step, once I've got an implementation in place, is we actually simulate these measles epidemics to really answer the questions that I've already outlined. So as we can see here, I used a basic SEIR metapopulation model. And what a SEIR population model essentially does is it compartmentalizes the population into 4 groups. We have a susceptible population given by S, an infected but not infectious population given by E, an infectious population given by I, and a recovered population given by R. And essentially each individual occupies one of these positions and moves from one position to the next according to whether they're infected by someone or whether they recover and so forth. Given sort of the availability of data on measles epidemics or past measles epidemics, the latency period and recovery period, which I have here as 1 over sigma and 1 over gamma, about 7 days, and they're pretty easily estimated. It's consistent across epidemics regardless of geographical region for the most part. What is different and really context specific is these beta IJs that we have here. And the beta IJs essentially characterize the transmission rate between one district to the next. So a higher transmission rate between district J and district I essentially means that an infected person in population J is very likely to infect another person in population I. So the difficulty was trying to parameterize this. And we did so via essentially co-location data given by Facebook's Data for Good project. And this co-location data essentially gives you the probability that any 2 individuals from 2 different districts are going to be in the same place at any point in time. Informally, essentially we have here the co-location data as directly proportional to chance of contact. And for particular sort of contact-driven transmission models, the R0 values, or the transmission rates between 2 different districts, tends to be proportional to these co-location probabilities. And this is essentially what we have here. And what I did was I just scaled a particular R0 value, which we characterize around 18, which is typical for measles epidemics, depending on the region. And we scaled that according to the co-location probability times by the population that is driving this co-location probability. And essentially what you get is a higher R0 IJ value essentially means that there's a high risk of a person in population J infecting a person in population I. So this was essentially our first step, what we have here. And why this was so important was there's generally very little data to characterize mobility patterns between populations. And trying to parameterize the model according to the data that we did have, which was the Facebook population data, was actually quite difficult. But once we had that running and we had the census data to give accurate estimations on population density and area, we can move on to, I guess, the second point, which is sort of visualizing this and working out an efficient way of simulating it. To give you just a general sense of what the data looked like and what our model was sort of predicting, I provided two sort of visualizations. The top one, which we have here, essentially maps intracity as our inter-province and inter-province connectivity. So the darker lines essentially means that two districts are more strongly connected by mobility patterns, and a weaker color means they're less connected. And what we can see here, which is a little difficult, I guess, given the resolution, is that we have clusters, which essentially means that we have clusters of dark regions, which indicate that we have strong intra-province connectivity, but weak inter-province connectivity. And particularly dark are the transportation centers of Hanoi, Ho Chi Minh, and Da Nang, which is typically expected. Another interesting sort of visualization is this risk of infection measure that I have here. And this risk of infection essentially is a measure of how likely someone is to get infected in that population, with the darker regions being a higher probability. And we see here is Ho Chi Minh and Hanoi essentially are clusters of dark regions, which suggests that people in those regions have a very high risk of infection. Once the visualization of this data was done and it was generally consistent with our expectations, you could move on to the simulation of the model. Though I didn't get to the chance to sort of provide the model in here, as a general description, I used an approximate stochastic algorithm, something called tau leaping, which was introduced in 2001 by Gillespie. And essentially what it does is it runs sort of a Markov chain model where at each point in time we have some sort of event, and these events change the number of individuals in each of these compartments we have here in the SEIR compartments. And by doing that over a certain time frame, we can simulate some sort of stochastic evolution of the measles epidemic. And really why we chose this approximate tau leaping algorithm was because given the large data set and the large number of districts, it wasn't really feasible to try an exact stochastic algorithm. And the exact stochastic plus deterministic algorithms that we tried also didn't really compensate for the loss of accuracy that you typically see in deterministic models. So it was made a decision that we use an approximate stochastic model to simulate this efficiently. Once this was complete, though, we looked to actually simulating this model across Vietnam. And unfortunately, due to time constraints of the project, I wasn't able to do an extensive work on this because computational barriers were still in place, and we still had to think about, well, how do we efficiently compute the probabilities that we want to answer the questions that I posed earlier. So our next steps, which I've outlined here, essentially, well, how do we modify the simulator to scale with larger population sizes and a greater number of districts? And after we can solve that problem, we can move on to, well, actually simulating the model yet again, but across the entire Vietnam, to really assess the efficacy of different vaccination protocols. And I'm currently working on that with Dr. Choisey, and I plan to work on that in the future as well, given how I think relevant it is to the current pandemic landscape. So in conclusion, though, I would really like to sort of thank, I guess, Dr. Mark Choisey for his assistance in advising throughout this project, and also sort of OCRU and the Center of Health and Wellbeing for sort of providing support throughout the period. Thank you so much.